All right, next up is lipids, and we are going to cover three different kinds of lipids, oils and fats, and phospholipids, and cholesterol. So each one is going to have a slightly different structure or very different structure, and then each one is going to have its own function within the body. The reason why they're all linked together as lipids is that they are all water insoluble. There should be a water in there. There we go. All water insoluble, which means they are hydrophobic. They don't like being in water. So we are going to start with fats and oils. So this is like your basic animal fat, like lard, chicken fat, beef, olive oil, corn oil, anything that is, a fat or oil in your diet. They are called triglycerides because they are made starting with, I can't find my cursor. Oh, that's why, hold on. This glycerol head group here, and then to that you add 3 fatty acid chains. And you'll notice that this is also a dehydration synthesis reaction. I forgot to point out when we were doing the carbs, and I don't have the picture to show it, but carbohydrates are linked together through dehydration synthesis. So if I come here, let's say you wanted to put glucose and fructose together to make sucrose. You take away this OH and that H, and you get, it won't go to the next slide, there we are, this O linkage between the two. So glycogen is made by dehydration synthesis, and then if you want to break down glycogen into its glucose molecules, that is hydrolysis. So those two reactions are key to making your macromolecules. DNA is a little different, so we won't talk about the chemistry of the bond that holds your phosphate sugar backbone together. So here you are. This is a triglyceride or fat, a glycerol head group with 3 fatty acid tails, sometimes referred to as hydrocarbons. But they're called acids because when they're in this state here, this OH group can let go of that H+, and then it becomes O-, and it's releasing hydrogen ions into the solution, which is increasing the hydrogen ion content, decreasing the pH, thus making it an depending on the nature of the fatty acid tails or the hydrocarbon tails, the fats take on different physical properties. So if all of your carbon molecules have the maximum number of hydrogens stuck to them, 2 hydrogens on each carbon, that is called saturated, so it is saturated with hydrogen. If some of the carbons are lacking hydrogens and form double bonds with each other, that is called unsaturated. It is these unsaturated fats that are a little bit healthier. So the way it works is that if you have all saturated fat, like these here, the hydrocarbon tails are all straight, and that means that the molecules occupy a little bit less space and they can pack very tightly together. This is why animal fat is a solid at room temperature. So like lard or whatever, bacon fat, beef fat, solid at room temperature. If you have lots of, what's the word I'm looking for? Unsaturated fatty acids, then the tails are kind of crooked and the fats can't pack as closely together. And this is why plant fats or oils tend to be liquids at room temperature. So olive oil, corn oil, canola oil. And that makes them just a little bit healthier. All right, and then so next up, if it'll advance, there we go, is the function of triglycerides. They do a lot of different things. They do help absorb lipid-soluble vitamins. This is why it's a good idea to have like some olive oil or oil of some sort in your salad dressing, so that lipid-soluble vitamins can be absorbed with the oil. Fat, your subcutaneous fat, serves as thermal insulation, and your body uses fat as a shock absorption and a protective barrier as well. So there are fat pads behind your eyes that keep your eyes from bouncing around too much, and there's some fat packed around your heart and your kidneys. But for us, physiologically, we are going to primarily think of fat as your long-term energy storage, right? So if you have ingested more calories than you know you're going to eat in a day, or more than your daily calorie budget, instead of storing that excess glucose as glycogen, it is going to be converted into fat. So this is what your body does with the energy that it knows it's not going to use every day. So this is why we call fat long-term energy storage, and then glycogen is short-term energy storage. Then the second lipid is phospholipids. These are very similar in structure to fats and oils. So you start with your glycerol head group, and this picture also got fuzzy, but here's 1, 2, 3 carbons on your glycerol, and instead of having a third fatty acid chain on your glycerol, there is this phosphate containing head group here. The important thing to note about this head group is that this negative charge right here, this full negative charge, makes it very polar. So you have a molecule with one side that is nonpolar, and I forgot to point that out when we were doing the fatty acids, right? These are all CH2, CH2, CH2. Carbon and hydrogen form nonpolar bonds, so they share the electrons equally, meaning there are no partial charges on these molecules. So when you put this molecule in water, water excludes it from the solution. It pushes it away because it can't hydrogen bond with any of the water molecules. Here you have a molecule that has one end that can hydrogen bond and another end that can't. The primary function of phospholipids is that they are your major ingredient in cell membranes. So the way you're supposed to look at this here is that this is inside the cell, this is outside the cell. You want to remember that both of these environments, out and in, are watery. So your whole body is basically a sack of water. So the way the phospholipids arrange themselves, if you notice, all the head groups are here. Those are polar. So you have one layer of phospholipids with the head group facing out towards the water, and then another layer of phospholipids down here with the head group facing in the cell towards the watery cytoplasm inside the cell. So it is what is called the phospholipid bilayer, and this is the basis upon which your cell membranes are built. So you start with phospholipids, and then you add, if you look here, there are some proteins, and then here's some cholesterol, which we're going to get to next. This is cholesterol. You will note it doesn't look anything like lipids or phospholipids, or it doesn't look anything like a triglyceride or a phospholipid. It is these 4 interlocking rings. This chemistry is a little bit beyond us, but what you want to know is that these ring structures are very good at sharing electrons, which means this is a very nonpolar molecule, even though there's a little OH group hanging off the side, which theoretically is a little polar. Because the oxygen can share so well with this ring structure, it still ends up being a nonpolar molecule. So they are extremely hydrophobic. We are going to have 2 different major functions for cholesterol. One, cholesterol serves as the precursor for steroid hormones. So this is estrogen, testosterone, cortisol, aldosterone. So it's not necessarily the steroids that you think of as performance-enhancing drugs. There is a subclass of steroids, androgens like testosterone, that do cause muscle mass increase, that are performance-enhancing drugs. But there are also a whole host of other hormones derived from cholesterol that are steroids that have nothing to do with muscle growth. So corticosterone, cortisol, aldosterone, estradiol, estrogen, and progesterone all do not regulate muscle growth. That's just testosterone. But they're all similar to cholesterol. So your body starts with cholesterol, modifies it, and this is how it makes all of your different steroid hormones. Then, cholesterol is also a minor component in cell membranes. So there's cholesterol molecules here and there interspersed throughout the cell membrane. What this does is affect how stiff or fluid or flexible the cell membrane is. As I recall, more cholesterol makes it stiffer. But I always forget because it's been a while since I've studied the cell membrane mechanics. So you just want to know those two things about cholesterol. And we will stop there, short at 11 minutes for lipids, because we're going to do proteins next, and proteins is kind of long.